Hello, everybody, and welcome to the experimental design lecture here in the School of Engineering in the Autonomous University of the State of Mexico. Today, which is Monday, the 23rd of March 2026, we are going to talk a little bit about the classification of experiments and the treatment design. So I am going to share with you my screen. Okay. 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 So let us start. Mm, 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 mm. Okay. So today is 23rd March 2026. So the topics for today are, on the one hand, we are going to study the classification of experiments. And in the second term, we are going to study the treatment design. So these are the two general topics. So according with our lecture program, the objective for the first topic is, let me here. Okay. The objective for the first part of the lecture is to categorize, let me put it here, categorize the experiments designed based on their objectives. And we have here three different kind of experiments. We have a screening, we have a characterization, and we can have optimization. The idea is to select the most efficient structure for the different stages of the artificial intelligence system development life cycle. Okay. And for the second topic, we have the following objective. I am going to put it here. Okay. Which is we are going to define the levels and ranges of the independent factors or treatments based on physical knowledge of the system and experimental objectives to maximize the information density of the captured data. So it may seem that these two topics are very easy to learn, but it is important for us to understand actually why it is important to classify our experiments and the number of treatments that we are going to establish prior to starting our experiments. So, first of all, let me put here the the concepts. So here we are going to explain the concepts. So in the first place, we have the screening. So in the screening, we have to identify the important variables. So when I have to design an experiment, the first step is to see what are the important variables. One common mistake that is normally present in the design of experiments is that we are analyzing variables that at the end of the day, they are not very important. And the reason why we could get in this trap is because we didn't screen at the beginning of the experiment what are the important variables for my experiment. So if I just start doing the experiment, but I don't have any planification prior to this step, I can have this error. So at the very beginning, I have to identify what are the important variables. For instance, if you remember the airplane example, so in the airplane example, let us put it here. Uh, 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 mm, let's put bullet point. Okay. In the airplane example, the question here will be, does wing size matter? So we should ask ourselves whether the size of the wing is important, is an important variable. And that will be in the very first step, which is the screening phase, okay? Well, let's go to the second. The second point has to do with characterization. So we put here characterization. And here the idea is to understand the behavior. Again, if we take the airplane example, so we can say in the airplane example, the question will be, how does angle affect distance? So if I throw the airplane, let's say in one angle, I can reach some distance. But if I modify the angle and I throw it again, then I can reach a longer distance, for instance, okay? But what happens if I continue modifying the angle? So I am going to reach different distances, okay? So this characterization of this variable, the angle, I have to select different angles, for instance, 15 degrees, 30 degrees, 45 degrees, 60 degrees, and so on, in order to characterize this variable, okay? And the third point here, which is important, has to do with the optimization. So let me write it down here, optimization, okay? So here, the idea is to find the best combination of variables. That is the optimization stage. So here, my question would be, I'm going to put a bullet point, okay? In the airplane example, the question will be, what gives maximum distance? Okay, if I am able to identify what is the correct combination of variables in order for me to reach the longest distance, then I am optimizing this system. Okay, so let us now talk about the treatment design. The treatment design. Okay. So the treatment design, it's related with the space that I am going to choose between each of the values of one variable. For instance, if I am studying the angle, so I have to select two, three, four, or more different angles. But here you should be very careful about the following. If values are too close, then you have no learning. Okay? If I have to choose some angles and I choose 10 degrees, 11, 12, 14, 15, they are very close together. So I am not going to learn a lot about this variable, right? Why? Because they are very close. 10, 11, 12, 13, 14. So they have just one unit apart from each other. So that is not a good design because I am analyzing just a very small part of the complete range that I could be studying. So another point, if values do not include extremes, then the model fails. Okay? So let's go to the airplane example. So for instance, if I am just testing, let me put this bullet point here. If I am only testing two different angles, let's say 20 degrees and 25 degrees. So this is useless. This is not very useful. It is useless, okay? Another point, if I am not testing extreme angles, then artificial intelligence fails in real world. So let me put here a table. I am going to save this. I am going to introduce a table. So this is 2, and this is rows number 7. And we are going to compare. Here I am going to put the experimental design. And I am going to put here the artificial intelligence. In order for you to realize how they are correlated, okay? So in artificial design, in experimental design, we are talking about factors, and in artificial intelligence, we are talking about features, okay? Let me put this table. Okay. In experimental design, we are talking about levels, and here in artificial intelligence, we are talking about feature values. Okay. Here in experimental design, we are talking about the screening, and here in artificial intelligence, we are talking about feature selection. Then we move to characterization, and here we have to put model learning. Then we are talking about optimization, which is the parameter tuning. And finally, we are talking about the treatment branch, which in artificial intelligence would be the training data distribution. Okay. So this is how you, as artificial intelligence engineering, are going to use the experimental design in practice in real life. Okay, so you have to design an experiment, as I said, but the equivalent in artificial intelligence, they are very similar, right? They are very similar because they are looking for a model, a mathematical model that can predict the behavior of some system. Okay, for instance, in the Netflix, when somebody looks for a movie, so if it is an action movie, let's suppose that this user is looking for the James Bond uh, 007. Okay, so this is an action movie. If this user um, looks for this James Bond movie, then the system, the artificial intelligence system, is going to propose similar movies to this user. I don't know, perhaps another film of James Bond, or perhaps something related with uh, action movies, such as, well, very old movies that I saw when I was a kid: Terminator, Rambo, Rocky, and so on, uh, or the Avengers movies, perhaps, because they are related, and they are the model, the artificial intelligence model, is predicting the behavior and the likes of this user, right? But perhaps somebody is asking for cartoon movies, okay, Disney. So the artificial intelligence model is going to propose, based on this characteristic, different movies, Disney movies, such as Toy Story 1, Toy Story 2, Ratatouille, the I don't know, Aladdin, and so on. Okay, so this is the correlation between experimental design and the artificial intelligence models. Okay, so here we can say that a bad experiment produces bad data, and bad data produces a bad AI model, artificial intelligence model. Okay. Okay, so I am going to put here, um, let's go back to our airplane design. So let me see. Okay, I am going to put here airplane example. So here. So as you can see in this photograph, I have got three different models of airplanes, right? All of them have different characteristics, different features. And again, uh, when I am designing these airplanes, I have to be very careful, because let me put a different here. When I am designing these airplanes, I have to record all the variables, okay? So as you can see here in this photograph, in these boxes behind, I have so many different airplanes, okay? But these three, imagine that these three are the top three in distance. So for instance, the airplane A um, could fly 123 centimeters, okay? Plane B could fly the distance of 143.5 centimeters. And finally, plane C could fly a distance of 132 centimeters, okay? And as you can see, they all have different shapes, right? They have different shapes. So let me put here this table. I'm going to put the table here. So let's see the type of experiment. Type of experiment. Here we are going to put the airplane example. And here we are going to put the artificial intelligence. Okay. So again, let me put this format to the table. Okay. So in the screening, as I said earlier on, the question would be, does wing size matter? So is it important the size of the wing? That will be the question. So I am choosing a feature selection. So I am establishing that wing size is a feature that I have to study in my airplane in order to determine whether it is important in the final distance that the airplane flew. In the characterization, the question will be, how does angle affect distance? Okay, that will be the question. So here I am going to choose different angles, but it would be something like, instead of 10, 11, 12, 13, and 14, which are very close together, I would have to choose more separated values. Okay, for instance, I could choose 10, 20, 30, 40, 50, and so on. Okay, they are more separated in order for me to determine whether there is a difference in the distance based on the angle that I am throwing the airplane. So this can help me. This is a learning function. Okay. And when I am in the optimization, the question would be, what combination flies best in the airplane example, okay? Here I am tuning the airplane. So I already know that the wing size and the angle matter in order to get the longer distance, right? So I have to choose this combination in order to design an optimal airplane. Okay, so this is the parameter tuning. Okay. I am going to put here a note. A common mistake is optimizing something that doesn't matter. So be very careful because sometimes we are looking at some variables, but actually don't matter. Okay, they don't have any influence in the, for instance, in this case, in the distance, okay, of the airplane. So we have to be very, very, very careful about that. Okay. So when I am in the screening stage, for instance, to we have two different wing size. Wing size. We could have small and large. Okay, that would be two different. This variable can assume two different values, small and large. Okay. What about the launch angle? The launch angle could have, again, if it is not quantitative but qualitative, I can have low angle and high angle, okay? So this is translated in the execution. If I have these two different variables and each of them has these two different states, wing size is small and large and launch angle is low and high, I can have four different experiments. So let me put this down. Here, here, okay. So let's put this bullet point. So this is four experiments. Okay, which it will be small, low. It will be small, high. It will be large, low, and large, high. Okay, okay. Well, so far, do you have any question? Okay. So let us carry out an activity. So I am going to let you an activity. You are going to put in this table experiment distance. So here we have the wing size and the angle. So it will be small, low, small, high, large, low, and large, high. So what I would like you to do is the following. Please uh, manufacture 4 different airplanes, but each of these 4 different airplanes will have to respond to these 4 different experiments. Okay, so you are going to manufacture an airplane with the small wings, and you are going to throw it in a low angle. Okay, so it is practically horizontal. Okay, and then you are going to use a high angle, let's say 45 degrees. So you are going to throw it again, and you are going to measure the distance. And then you are going to manufacture a airplane with large wings. So for instance, here you have these examples, and you are going to record here the distance, okay? And the question that I would like you to answer is the following. Which factor mattered most? Wing, wing size, or the angle? Which of these 2 factors matter the most in order for the airplane to fly the longest? Okay, so let us carry out this activity. So individually first, you are going to have 10 minutes. So if you are at home, use 4 different piece of paper bond, in order to manufacture these four airplanes and throw them. But make sure that you throw them from the very similar point in order to record the distance. And you are going to put these distances in this table, okay? So take 10 minutes, please, in order to carry out. So it is 10 to 5 p.m. So we are coming back with the results in 10 minutes. At 5 p.m., I am coming back. So go ahead. If you have any questions, please ask. Otherwise, I will see you in 10 minutes time, please. So manufacture these 4 airplanes at home and then record the distance. Okay? Okay, see you in 10 minutes. Hello, everyone again. How are you doing? Have you already finished?
No yet, teacher.
Okay. Can anybody help me, please? What I would like to do is to put Excel, uh, but the idea is that everybody can record their data in this Excel. I think that it is possible through Google Drive, but I don't know how to do it. So, can anybody help me? So, the idea is to have an Excel, and each of you are going to record the distances at the same time in this Excel. Uh, Anybody knows how to do that? Okay, let me try to do it. So here I will have to put. Let me do it in this manner. Okay. So I will put experiment. Okay. Small, low, then small, high, then large, low. Let us put it in this way better. Small, low, small, high, large, low, large, high. Okay, okay. Mm, mm, mm. No, no. Okay. 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 Okay, send the link. Yes. Yes, yes, yes. Let me, I am going to put here. Okay. So these are experimental design lecture 23 March 2026. Okay. Okay. And Mhm. Okay. Mm, mm, mm. Okay. So how can I share this with you? Okay. I am sending the link to this file, and you are going to see the surname. So can you please verify if it is possible to access this Excel file through the link? And you are going to record here the distances.
Teacher,
Mm-hmm. Yes.
the file asked me for permission.
Okay. How can I? Let me see. Let me see if I can. Okay, let me put again. I don't know whether it is exactly the same link. Apparently, you are logging in already, right?
Teacher, but we can just read the text, not
Ju-
edit.
Okay. So let me see. How can I modify that? Uh, uh.
You should click on the share button
Here,
in the other side.
in the other side,
What is the Earth?
the Earth.
En compartir, profe.
Compartir. Here, okay, the Earth. Okay, yes.
Y ahí donde dice cualquier usuario que tenga el vínculo, ahí en lector le cambia a editor.
Okay, editor. Okay, ready. Shall I upgrade the link or is exactly the same link?
It's the same, but you
Okay, with
change the.
the new permission, okay? Okay, let me put it here. This is the okay. Okay. And you write now?
Yes, teacher.
Okay, perfect. Okay, so please record your results here in this table.
Teacher,
Yes,
I have a question. We
yes.
are two Hernandez.
Okay, let me see. The first one is Omar, and the second one is Sebastian.
Okay, thank you.
And the same happened with Romero. The first one is Angel, and the second one is Axel. And with Sanchez, the first one is Miguel, and the second one is Cesar. Valdez, the first one Alexis, and the second one Leonardo. Okay. Okay, I can see the results here. Okay.
Teacher,
Yes.
bueno, me pidió descargar como una hoja de esas de Google, pero cuando me meto me manda uno que dice diaporama o algo así, no me manda directamente esa tabla.
Okay.
Pero
Try
a mí,
the last link. Ajá.
a mí no me da chance de escribir. Bueno, de hecho no me deja ni acceder a la hoja. No sé si podría volver a mandar el link.
Yes, of course.
¿Por qué? Gracias.
No problem. I am going to send the link again. Okay. Try this one. Were you able to access? I don't know whether, for instance, what I am looking here is that there are 10 people working together at the same time here in this part. So perhaps there is a limit. But I don't know. Okay, so let us analyze the data that we already have. So look, as you can see here, the question is again, which factor mattered most, the wing size or the angle? What will be your answer?
I think the angle.
The angle, okay. Is there any other answer?
Yeah, I think it's the wing size.
Okay.
Yeah, I think both, but angle is more important, maybe.
Oh, okay. We will have to wait until the very end when this table is complete in order to determine which one of the two matters the most, okay? But apparently the two variables are important, okay? Not only the wing size, but also the angle. So let me share again the word. Okay, so the two, let's write down here, the two variables matter. Wing size and angle. Okay. Here's one important point. Important point. So in first place, we should say in this experiment, in this particular experiment, only extreme values are used. So you have to small and large, but you have low and high. Okay, so we are using the extreme values. So here the goal is to eliminate irrelevant variables. So in the screening, you use two widely spaced levels. Okay. Okay. Now let's move on to the characterization activity 2. This is a screening. I am going to put in bold. This is a screening. And the following would be characterization. So here, let's copy this. Characterization. In large angle, you can have, for instance, 15 degrees. You can have 30 degrees. you can have 45 degrees, and you can have 60 degrees, okay? So here it is important to check the following. Let me put look, if I have only 2 points, for instance, low angle, let's say 0 degrees, and a high angle, 45 degrees, I only have 2 points. So I have 1 point in the low level and another point in the high level, okay? And when I put together these points, what I am going to get is a line, a regression line. You can see here, this line is the blue one, okay? With only 2 points, I can define this line, and the prediction will be somewhere here, okay? This is going to be the prediction at the very top of this line. But when I have more points, I have, for instance, 15 degrees, then 30, then 45, then 60, and so on. I can see this is a curve, okay? It could be, this is the true regression function, okay? And the prediction is no longer up here, but here in this point, okay? So it is better to have more points because I can actually discover the real shape of the function, okay? I can have the real shape of the function. So that's why it is important here in the characterization to increase the number of angles, for instance. I can have 15, 30, 45, 60, 60 degrees, okay? So let me put another image here down there. So for instance, here, okay, I'm going to put this. Look, in this case, you can interpolate in the range between the minimum and the maximum value. That is something valid in experimental design. It is okay to interpolate. So that means that I can deduce the values that are in the range that I am studying. But it is not so correct to extrapolate, okay? To try to predict values that are outside the range that I established at the beginning. So for instance, here, if this value is the minimum and this value is the maximum, all the blue points here are correct, but the red ones, the red points that are on the left-hand side, which are extrapolated, or the red ones that are on the right-hand side, it is not correct to use these extrapolated values, okay? Because the model is not so efficient, and you can see it here, okay? For instance, you could predict this very high point, and it has nothing to do with the actual shape of the curve, okay? The actual shape is a curve. It has got a peak here, but then it goes down, okay? So the correct value would be in the red line, not in the blue one. In the line, in the straight line is not correct, but in the curved one, okay? That is the correct thing to do, okay? So that's why we need to increase the number of measurements in order to have a better approximation to the shape of these regression lines. Okay, so here we can say that in the range matters. Okay, so the range matters. It is important to consider the range. So a bad design will only consider, let's say, 20 degrees and 30 degrees, for instance. But a good design we consider 10 degrees, 20 degrees, 30 degrees, and so on, perhaps until 70 degrees and 80 degrees, okay? What we can say here is that the model is only as good as the range of data it has seen. Okay? What other point is important? So if you have levels too close, this is useless, as I said already. Useless data, okay? For example, if you have 20 degrees, 21 degrees, 22 degrees, there is practically no variation because they are very close together. So here you cannot distinguish the variation because they are very close together. Okay? So for instance, here, if I am just looking at very close points, I cannot determine whether there is an important variation. But what happens when I use a value that is separated? For instance, this maximum is separated for the minimum, so I can already see this variation. Because look, if I am just playing here in this small range, it is practically the same. It is you cannot perceive the variation, but if you use an extreme value, for instance, you can actually see this variation. And here, what else can we say? So, in artificial intelligence, interpolation is safe, extrapolation is dangerous. Okay? Okay. So do you have any question? Okay. I am going to share this MATLAB. So I have here a script in the MATLAB related with this airplane experiment. Okay. And I am going to show you some of the results. So you don't have to worry now about how the model works and how it is built. We are going to see that in detail in the following subjects of our experimental design class, okay? For now, what I would like to show you is how this combination of variables and things are reflected in some graphics. So when you are analyzing these graphics, you can see the difference between having just two or three, for instance, angles, or two or three different wing sizes, okay? So let us run this script. So here we go. So here it says enter vector of wing width. So for instance, let us imagine that we only try with two different uh, widths. For instance, it could be 5 and 15. Okay, that is the centimeters. Okay, that is the width of the wings. Then enter the vector of launch angles. Let us suppose that we only have two different angles. Imagine that we have 15 degrees on the one hand, and let's suppose 60 degrees, okay? We have only two, this will be equivalent to the experiment that you carried out at home, okay? With you only had two different states or two different values for the variables, low and high, and small and large, okay? So let us run. Okay. Let me show you the graph. Okay, this is the result, okay? This is a response surface for the paper airplane distance. I am going to copy this figure and I am going to put it in the Word MATLAB example. Okay, so let me just, I'm going to explain this to you. So let me just put this. Okay. Okay. Look, you have in the three different axes. So in one axle, you have the wing width, okay, which is this axle here. In the other axle, you have the launch angle. You can measure that in degrees and the wing width in centimeters. And in the vertical axle, you have the distance, okay, the distance. So if you have launch angle, which is small, in this case, it is 15 degrees, and the wing width is as well small, just 5 centimeters, you cannot expect the airplane to fly a long distance, okay? So look, with 5 in the wing width and 15 in the launch angle, you can only fly 0.98 meters. So it is 98 centimeters, okay? You can see it here in this box, okay? In this white box. What happened? If you have now in this point here 15 centimeters in the wing width and the angle is 15 as well, you can fly a little bit more, okay? Which is 1 meter and 1 centimeter approximately. But what happened if you have in this point here, if you have the wing width, which is 5 centimeters, but the angle now is 60 degrees. So the distance that you can reach is now 2.15, okay? 2 meters and 15 centimeters, okay? And what is the best? The best combination in this case is when you have a wing width of 15 centimeters on the one hand, and on the other hand, you have a launch angle of 60 degrees. In this case, you can reach more than 4 meters, okay, of distance. It is 4 meters and 15 centimeters, okay? So this is the way in which we are analyzing these results of the experiment, okay? So let's suppose that these are the distances that you have uh, in the table, okay? In the table that I shared to you. I am going to write it down in the WhatsApp. So let me put here and here. So for the first combination, so small, low, you have a distance here in this MATLAB experiment, okay? Small, you have 0.98. I am going to record this, okay? Then the second combination, you have a small, and you have high angle. So small wings and high angle. Here you have 2.15. Okay, so I am writing down 2.15. Okay, then the next combination, it will be large and low. In this case, you have 1.01. And the last combination would be large and high. Is the best. In this case, is the maximum value. You have 4.15. Okay, I am writing down in the WhatsApp group. So let's go back. Okay. 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 So look, let us put here. Okay, I am going to put here these values that I calculated with the MATLAB routine. So in the small low, it is 0.98. Then small high, it is 2.15. Large low, it is 1.01. And large and high, it is 4.15. Okay. This is recorded in meters. So if I can put this, if I want to put this in centimeters, it should be 98, 215, 101, and 415 centimeters. Okay. So let us compare with your results. Okay. So let us put here another. So the first place, the longest distance, it is this combination, that is the longer. The second is this one. Third place, it is here. And this is the fourth place. Okay, this is the rank. And this is the MATLAB result. Okay. So here we are. So let us compare, for instance. Here, Carvajal. The first place was this again, second, third. Practically, it is practically the same. You have this as well as the first, as the longest, right? Colleen has, again, this was the first place, so the longest. Then the second, the third, and fourth. This is the same result for Gutierrez, the two of them. Here, for instance, here Hernandez has got the first place. Again, this combination, large and high. The second was large and low. The third was small and low. So look how some of you have similar results, right? But what I can see here is that most of you, these two, large and low and large and high, were the longest, right? These two were the longest. So let us try with a different combination in order for you to see this, okay? Okay. Here. So I am going to share again my MATLAB. Okay. So let us run this script again. So now imagine that I have more different wing widths. For instance, I can have 5, I can have 10, I can have 15 and 20. 4 different, okay? And let us imagine that I have these different angles again. So it will be 15, 30 degrees, 45, and 60 degrees, okay? So let us run this script with this data. Okay, so I am going to show you the result. I am going to share. Look, it has changed, okay? You have more combinations. So let me put this in the Word. And I will explain to you this new figure. Okay. Okay, and I want going to copy this figure, copy figure, and I am going to put it in the Word file. Okay. 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 Look, when I have more combinations, I can predict better the result, okay, of the experiment. For instance, at the very beginning, do you remember the wing in the first experiment? We have 5 and 15. But look what happened in this second experiment, okay? If you have 5, but combine it with the different angles, you have different results here, okay? And you have here the 15, okay? But here is a better distance that you can reach, okay? And at the beginning, you only had this point and this one, so you have a straight line in this case. But now, when you introduce a new value between these two extremes, you can now see that there is a better performance of the airplane if you have a wing width of 10, okay? 10 centimeters, okay? If you have 20 centimeters of width, it is going to be worst. It is not going to improve the behavior of the airplane, okay? But here you can improve a lot. Okay, what happened with the angle again? At the beginning, I only had these two different angles, which were 15 and 60 degrees, okay? But now I have introduced more angles. So look, here you have a better combination, okay? If you have 10 centimeters in wing width and 30 degrees of the launch angle, you can reach 10 meters, okay? You can reach 10 meters away. What happened here? You 9.3, and here in this 10.17. This is the best, this one, okay? So the best combination in this second experiment with more data, with more different airplanes, it is when you have 10 centimeters in the wing width and you have an angle of 60 degrees, okay? That is the best because you can reach 10.17 meters of distance, okay? So look, when you introduce more and more different values in this case, you can have a better approximation. Okay, your model is better. So let me go back to the Word. Okay. So this is the MATLAB example. In the first case, I just used 5 and 15. This is the wing width, okay? And I used, I am going to erase this example, just put the actual values. So this is just for me in the MATLAB to have an idea about the values, but here I can erase this. Okay, I have just 4 different experiments and my surface is very simple. It is very easy. Just have 4 extremes, okay? Small low, small high, large low, and large high. So only 4 different combinations. But what happened when I increase the number of wing widths and I increase the number of launch angles? Okay, so look, you have more combinations and you can predict better the behavior of this experiment. Okay, and let us carry out a third experiment. So I am going to save this. I am going to close this. And here we go. I am going to share again the MATLAB. Okay. So let us now run. But look, I am just going to have 10, 11, 12, 14, and 15. Oh, 13, sorry, 13 and 14. Okay. Let's put 15 as well. And in the case of the launch angles, again, I am going to have 30, 32, 34, 36, 38, and 40. Okay. As you can see, you have more different values, but they are very close together. So let me run this script. Okay, and I will show you the result. Here is the result, okay? Here is the result. So let me copy this in the Word. Okay, and I am going to copy the figure as well. So copy figure, and I am put it here in the Word. Okay. Let us analyze this new result, okay? So, and you can see, right, the blue, the color blue represents very small distances, and the yellow color represents long distances. Okay, so if we are looking here, so they are not changing a lot because this is very close together. So you have 10, 11, 12, 13, 14, 15. So look, here you have 8.99, 9.42, 7.97. If you see these values don't change a lot, okay? It is not like at the very beginning when I have less than 1 meter, and on the other side I had 4 meters. So it is a very high difference, right? In this case, they are very close together. Let us see, for instance, here I can see that it is 899, and here it is 8.38, so it is very close. And here it is 9.6, 10.3, 9.9, and this is 10.36. Okay, so which one is the maximum value? Let us see whether we can. I think that it is this point or this one. This one. It is 10.59. This is the best combination, okay, in this experiment. So it will be 11 in the wing width. It will be the angle, it will be 38. The launch angle, it will be 38. And the expected distance, it is 10.59. Okay, 10.59. Okay, so let me go back to the Word file. Okay. Very good. Let me put this smaller. Okay. So here you can see that it is not only about increasing the number of points, but you have to do it in an intelligent way. Okay. You should be very smart, because this is okay. This is 6 different points: 6, 10, 11, 12, 13, 14, and 15, but they are very close. What you should do is to use 10, 20, 30, and so on, okay? That they are widely apart in order for you to determine the best way to optimize this experiment, okay? Okay. So here, recommendation, we can put the following. Bad design, so it will be wing width here. This is an example, right? Wing width which is 9, 10, 11. They are very close. And the angle, if you have 30, 35, and 40, that will be a bad design. They are too close. There is no variation. And the model is useless. But in contrast, what would be a good design? Let me copy this here. So a good design is the one that has, for instance, 5, 15. It could be 5, 15, 10, 15. And the angles could be 10, 45, 60, for instance. Okay, this is a wide range. And you can capture the system variation. Okay. Okay, let us save this thing. Okay. Do you have any question?
No, teacher.
Okay. Well, this is today's lecture. I am going to put this in PDF format. Okay. 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 We are going to have the holidays the following week, and I am going to give you a homework to do. You are going to carry out an experiment, okay? So I will explain to you this experiment, but let us take some minutes, right? Some coffee break. So it is 10 past 6. I will see you in 10 minutes time. At 6:20, I am going to explain the homework to you, okay? You are going to carry out this activity in Teams. So please go back on time in order for me to explain to you the homework, okay? Thank you very much, everybody, and I will see you in 10 minutes. Okay. So as I was telling you, we're going to have this activity. I am going to share my screen. Mhm. Okay. So here we go. So this is the activity. It is called Mousetrap Card Design Challenge. It is going to be a challenge for you. And the objective of this challenge is you have to design, build, and optimize a mousetrap powered car using CD wheels that travels the maximum possible distance, applying principles of experimental design, screening, characterization, and optimization, and treatment design. Okay. I already shared with you in the chat of the Teams lectures note, the lectures note of today class, so you can have this file there. So, what is the engineering context? You are not just building a car; you are designing an experiment. Okay, keep that in mind. Your goal is not trial and error. Your goal is to generate useful data and make decisions like an artificial intelligence engineer. Okay. So this is part number one, the system understanding. So these are the system components. So this is the mouse trap. Do you remember Mickey Mouse or Tommy Jerry? There were a lot of mouse traps. So they put here cheese, and the mouse goes for the cheese, but then suddenly there is a spring in this mouse trap, and the spring uh, um, catches the mouse. Okay, so you are going to use this, and you are going to use CDs. Okay, do you remember CD when we used to play our music in the CD room? Well, here is the CD. Okay. So this is just an example on how your car will look like at the very end of the design process, okay? So the idea is that you have to use your creativity, your imagination, but not only that, but also you have to use the experimental design concepts that we have learned in this lecture uh, to design this car. Okay, that is the challenge. You have to design this car, and you have to put somehow you have to use this force in the spring of the mouse trap in order for the wheels to start working. So here is another example. So the idea is that you have to push the mouse trap towards back and the end of the axle, and here with the somehow you have to connect this part with the wheels, with the axle of the wheels, in order for the car to start moving. Okay. Here is another example. The design matters, obviously. You can have a pencil. For instance, this guy put a pencil here for the axles. Okay. He used some board and things like that. Okay. There are different examples. So you have to design to design all of this. Okay. You have to carry out different experiments in order for you to design the best car possible with the mouse trap. So here are some ideas how you can put together these parts of the car and the degrees and so on. Here is another example of how your car can look like. Okay, so let me uh, uh, let me see. Okay, before I continue, let me try to show you. 1 second. Some examples of my previous class. Uh, Let me see. Mm-mm. And I can show you. I can show you some examples. Just wait a minute, please. Okay. Here. Okay. So let me show you some examples. Mm, Here. This is real examples made in the School of Engineering. Here. These 4 cars were actually made by my students in a previous semester. I think it was in 2024, something like that, because I had the sabbatic year, so I didn't give any class during the 24B and 25A. I didn't give any class, but prior to that, they designed these different cars, right? Uh, they used these materials, as I was telling you, in order to build these cars. Okay. In fact, 1, 2, 3, 4, 5. There are 5 different cars here, as you can see. There are 5 different cars in this table. This is in the building G in the School of Engineering. Okay. So this is just to show you an example. And I think that I have got also a video. Let me see. If I have got this video. Okay. Yes, I have the video. Okay, let me, I am going to share with you this in the WhatsApp. WhatsApp. Okay. 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 Let's see. Here you can see we were trying this up there in the G building, and that is an example of how they behave. Okay, let me see if I have another video. Okay. Oops. Okay. Okay. Here we are. Yes, I have another video. I am going to share with you as well. Experimental design. Okay. Here we go. This is another video. Okay, well, this was edited, obviously, and it has got the sound of the machine. Okay. Okay. Well, that is the idea. Okay, that is the idea. So let me explain to you the steps. Okay. Okay. Well, as you can see, there are so many different models, different designs that you can actually build. So the idea here is not just to use your creativity, but also to apply the experimental design concepts in order for you to build, again, the best car possible. Okay? Well, what are the materials? So you are going to require one mouse trap, which is the energy source of the car, the CD wheels, the axles, a string, a lever arm, and a chassis. So look, here are some of the variables of the experiment, right? That you have to consider. For instance, the lever arm, which is this part of the car, this straight line you can see. You can play with the length, right? You can have 20 centimeters, 30, 40, and so on. Okay. You can also play with the length of the car. You can have a short car, as I show you in the photograph that I shared to you in the WhatsApp team, or you can have also the type of mousetrap, because there are different brands. Okay, not only one brand, but different brands. You can buy that in Garis, I think, or in Super Compras. You can buy these mousetraps, okay, or in some convenience store. Okay. So the experimental design, so you have to define the factors or the independent variables. And each team must select at least 3 factors. For instance, the lever arm length. You can decide whether to use short or long arm, okay? Or you can have actually values, right? 20, 30, 40 centimeters, okay? Another factor, it will be the wheel diameter, okay? You can have the actual CD or you can cut it somehow or use, there were, I think, mini CDs at some point that you could use, right? So you have to decide that. The axle thickness, again, you can use thin versus thick. The string length, the string, you have to decide whether you use short, long, or you can use different values. 10, 15, 20, 25, or 30 centimeters, for instance. And the weight, it could be light versus a heavy chassis. It could be a very heavy car or it could be a light car, okay? Okay. Then in the screening design, you have to identify which factors matter most. So at the beginning, in order to screen, just to give an idea, just choose two different levels, low, high, okay? And carry out some experiments in order for you to decide this is an important factor or this is not an important, okay? For instance, you can try the lever arm 10 and 30 centimeters to see whether this actually has an impact on the distance that your car moves, okay? Or the string length. You can use 50 centimeters or 150 centimeters. So in this part of the exercise, you have to decide what are the most important factors for your experimental design. So here, my recommendation is that you use widely spaced levels to detect significant factors because again, if you use the lever arm 10, 12, 14, 16, it is not so apart from each other. So you are not going to detect whether this is or not an important factor. Then in the characterization, here the goal is to understand how the system behaves. So here, what I will do is to select 1 or 2 important factors, but now you have to test more levels, not just 2. In the screening, okay, it's just the very first step. But in the characterization, you have to try more different levels, at least 4. It is like the exercise that we did now in the MATLAB, okay? We start increasing the number of levels and you could see how the figure was changing. So for instance, you can have these 4 different level arm and you use 10, 20, 30 or 40 centimeters and you record the distance that the car is moving. So here the key concept is the more levers are required to capture no linear relationship. Do you remember when we have just 4 combinations? It was a very simple shape of the response surface, okay? But when we were increasing the number of levels, it is more detailed. The shape of the surface is more detailed. Well, in the step 4, the optimization, your goal will be to find the best configuration of the car. What are these variables that matter the most? And how can you combine these variables in order for the car to move a long distance? So here you have to combine the best values from previous stages and perform the final test. So here the key concept is that optimization finds the best combination of factors. Then in the treatment design, this is a critical part. You have to use a wide range of values, okay? So a bad design, as I said, will be to use 20, 22, 24 centimeters. But a good design will be to have separate values, 10, 30, 50 centimeters, okay? That is the point of the treatment design, okay? Avoid clustered values. Again, if values are too close, you have no learning. And you have to include extreme conditions. A very long stream, a very short lever, for instance, a heavy versus light car, and so on. The model is only as good as the range of data it has seen, okay? Well, and here you have this phrase, this statement: interpolation is safe and extrapolation is dangerous. We already write down this on the lecture's note, okay? And you can record all the data in a table like this, okay? You carry out different experiments, 1, 2, 3, 4, 5, and so on. You can have different experiments, and you have to record exactly what were the variables that you were considering, and then you have to record as well the distance that the car moves. And if you have any observations, you can write it down here. Well, for the part 5, which is the results integration, you have to put all the results. Remember, you have to also develop. You are going to take photographs of the process, and you are going to record this in a Word file, and then you can put it in PDF file, okay? And we are going to analyze, you are going to present the results of your experiments in the following lecture, in the following class. And we are going to analyze which car performs better. Which factor had the biggest effect, and which design failed and why, okay? And the artificial intelligence reflection is what happens if your data only includes good design? What happens if you never test extreme cases? How would you an artificial intelligence model fail with poor data, okay? So in this challenge, you must present your design strategy, your data, your best car, because you are going to have different cars, right? You are going to experiment with different cars. So you are going to choose the very best car. And what was the engineering reasoning for developing that car, okay? Perhaps at the beginning, you don't have the best car because you are trying with some different cars, okay? So you are playing with the wheels, you are playing with the mousetrap, and so on. But when you have the design and you can see what are the best combination to get the best car, then you are going to build the best car, okay? What are the deliverables? Each team submits a PDF report which has the factors and their levels, the experimental design type, the data tables, the graphs, and the conclusions, okay? And here is the evaluation criteria. So what I am going to evaluate is the experimental design quality. It will have a weight of 30%, the data analysis 25%, engineering reasoning again 25, and performance. The distance is going to have the 20% of the total weight of the experiment. Okay, so in conclusion, the best car is not built by luck, it is built by good experimental design. Okay, I am going to share this file with you. Let me put it here. Attach file. Okay, let me put this here, attach file. From this computer. Okay, send. You are going to receive now the challenge, and let me share with you in the WhatsApp. Okay. Okay. Okay, so I am going to open here in the okay. Okay. So this is going to be Mousetrap Card Design Challenge. Okay. 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 Mouse Trap Card Design Challenge. This is for the following lecture, which is April the 6th, 26. Okay. So it will be okay, which is 15. Okay. Okay. For the teams, please carry out this activity. I am going to write it in the WhatsApp. Okay. You can choose your classmates, right? I am not going to tell you the people who you are going to work. You choose your classmate. It will be 5 teams of 5 people. Okay, 5 teams of 5 people. I am writing down this in the WhatsApp for the mouse trap car challenge. Five teams of 5 people. Okay. 5 teams of 5 people. Okay. Okay. Okay, guys, do you have any question about what we are going to do?
No, teacher.
Okay, you are going to create your own team, 5 people in each team, and we are 25 in the class, so it will be 5 teams of 5 people. And you are going to develop this thing. And remember to write down everything. You should apply everything that we have seen so far in the lecture in order for you to have a very good design of this mousetrap car. Okay? Okay. If there is no questions, then I am going to stop here the recording of the lecture. But give me a second in order for me to pass list. Okay? Thank you very much for your attention.